This is indeed an attempt to literally use method of quantum field theory in turbulence, and it illustrates both advantages and the complications which appear on this way. But for this, as already was discussed yesterday, it's very much pays to look at turbulence a bit wider and consider many turbulences, because when we look at field theory, we have many field theories, and we have very effective in 2D, very effective, but generally still ability to classify them into universality classes and say that these classes of field theories are different from Z classes. And from this viewpoint, the same we can do with critical phenomena. We can classify critical phenomena into different universality classes, and they are very different. And on the other hand, the Hamiltonians, Lagrangians, equations of motions could be very different, and yet system could belong to the same class. So in this sense, this work, which I which I think is the beginning of some approach, is an attempt to start doing similar things, namely classify. Let's say this turbulence will be like this, and that turbulence will be like that, belonging to different classes. And yet, because it's nice to be not only deductive, but also inductive and have a good example and illustration, I would from time to time return to this particular class of turbulent system. And this is a stormy sea. In what sense it's turbulence? Not because it's fluid. It's a system of waves, essentially. Vortices play not a big role here, but it's a system which deviated very far from equilibrium. So I would call turbulence a system which is where very many degrees of freedom are deviated from thermal equipartition. And this is a quintessential, it's very practical, interesting, and it's an example that we've all seen many times. And I'll try to return from time to it, and particularly, this is a sea as the wind is substantially lower, and this is substantially higher. Sometimes it could be that this is at the beginning when winds start to blow, and with time it grows. Not wind, the waving. And this is a really stormy sea. And so this is for students. I really not encourage professors to answer, but for younger people, this is a riddle. At the end, we'll return to it and we'll again discuss, is there anywhere quarks here, right? We're looking at analogy with quantum field theory. And in quantum field theory, we have these two quintessential examples, quantum electrodynamics and quantum chromodynamics. And we understand to what extent they are different. They're qualitatively different. Even though one we can describe to a very large extent, and another we still a lot of things hypothetical, but at least we understand the qualitative difference. So we would like to ask, is it like quantum electrodynamics or quantum chromodynamics, in the sense that there are many degrees of freedom, they are strongly interacting with each other over here, and probably weakly interacting with each other on the left. And yet we need to distinguish, okay? That's what my riddle. So what do you think? In which part there are quarks? Or there may be no quarks whatsoever? And except inside hadrons, which comprise this matter, which is called flow. Of course, there are quarks inside hadrons, but I mean analogy. Okay, so here is the work. My co-author is Vladimir Rosenhaus from Graduate Center at New York. And he is a former student of David Gross, and I'm a former student of Vladimir Zakharov. And to some extent, we try to bring two perspectives. One is classical field theoretical perspective from heroic age, where Sasha also participated, and other people, and from classical Hamiltonian system wave turbulence approach. And there is an archive, very rough draft. We are working on another one. So essentially what we'll be doing, as most of field theory is doing, we'll be doing renormalization. We'll be looking how actually the parameters of the system change because in the system there are many degrees of freedom. This is a strongly fluctuating system. And we'll start from a very, and I won't probably even go to other things. This is a Hamiltonian. You know, and when I was a student, they always say to us, stop talking, write Hamiltonian. So this here is a Hamiltonian. In particular, it describes waves of the water, spin waves, many other waves, cold atoms, etc. So it has a quadratic term with omega p. It's energy if you are a field theorist, or its frequency if you are a classical wave person. And it has lambda, which is coupling constant, which describes, generally, it depends on wave numbers. Everything happens in the Fourier, in a momentum space. P's are momenta. And there is an interaction, a simple scattering two waves into two waves. Okay. Generally, equations of motion, let's say of fluid mechanics, they contain a cubic term in the Hamiltonian and quadratic term in the equation. And yet, for, let's say, gravity waves, the cubic three-wave interaction are non-resonant, and using Poincaré normal forms, you can make canonical transformation and write your Hamiltonian in this form. Even incompressible fluid mechanics can be written as a Hamiltonian system with such a Hamiltonian, but with omega equal to 0. So if you write hydrodynamic equation in Klebs, there are so-called Klebs variables, you can write it's a Hamiltonian with quartic Hamiltonian with no quadratic term. So in this sense, this is still particular, but very generic class. And the equation of motions, as you can see, it contains linear term and it contains cubic term. So now what I want to do, I want to ask this omega and lambda, I just derive from equation of fluid mechanics. I know them exactly. This is a very principal difference which very often overlooked or misunderstood in trying to apply method of quantum field theory, is that in quantum field theory, generally, we don't know omega and lambda. The true values of omega and lambda somewhere at a very small lattice scale, Planck scale, we don't know. What are our field theories are effective theories, which we write at larger scales. And as we write them on a larger and larger scales, we understand that as we coarse grain or average over smaller scales, these parameters, omega and lambda, change. So in quantum field theory, usually our interest is how the interaction of many scales change our parameters from unknown values at somewhere fundamental things which we do not know. But we can measure them at a given scale, and then we can measure them at other given scale. So in a sense, we are interested how it changes because of these fluctuations, and fluctuations are there. Either we consider critical phenomena, which means in a critical point we have all these fluctuations, then we are interested how omega and lambda change with scale because of averaging over this fluctuation. Absolutely different situation we have in classical physics, in particular in turbulence. Omega and lambda are known exactly. What I'm interested in is what happens with omega and lambda when I excite turbulence. Namely, I have a quiet sea, I have a wave propagating over it. I ask what is the relation of its frequency to its wave number, it's omega. What is measured here? Now I have a stormy sea. I have a wave propagating over stormy sea. I ask how much its frequency changed comparing to the quiet sea. And the same thing, I have interaction of four waves. I can do it, just use two wave makers in a basin. I can send two waves, scatter one on another, measure the result, and measure lambda. And I can compute it from the equation of motion. Now I'm having my basin with a lot of waves running around, and I'm asking how it renormalizes my values. Again, I will be interested in how this renormalization depends on P's, on my wave numbers, on my scale. But it's important to know that I cannot renormalize out whatever divergency I encounter, saying that somewhere at a lattice scale, at small scale, somewhere my constant is such that at a given measurable scale, it gives me measurable quantity. There are no subtraction terms. There is no you know, subtracting out whatever you don't like. You know true lambdas and omega. This is really important thing. And okay, now let's go and renormalize. So first of all, what did we learn from quantum field theory, thanks to the heroic generation? This is, in a nutshell, the main formula which we get out of here. And it tells us the following things, that this lambda is really, this lambda is really is a function of k. And you take a, so you want to ask how it actually depends on this k. And you say that there are, of course, you assume that this lambda is somehow small. So you do perturbation theory, you start expanding. When you expand, you find out that it will be quadratic term, cubic term, quartic term. And in some cases, in a very, very particular class of cases, you can present this series as a geometric progression, or it's a little bit more complicated. Sometimes you need to do parquet, but somehow you may try to sum it. And the geometric progression will be summed into something like this. And then you say that what is really important and the first basic separation of field theories into two fundamental classes is the sign of lambda. If lambda is positive, then your interaction between many other waves, because every term of perturbation theory accounts for sextet interaction, 8 waves interaction, 10 waves interaction, and how it contributes the basic lambda, which is the magnitude or scattering amplitude of 4 waves. So what you find out that when beta is positive, it's decreasing. So existence of other modes or of other particles decreases the interaction of a given set of particles. And we call this situation screening, because that's what we first encountered in quantum electrodynamics. If you take 2 electrons and they interact, and you account for the fact that there are quantum fluctuations in between these 2 electrons, namely that this vacuum can produce electron and positron, but every electron would be produced a little bit shifted closer to positron, and every positron closer to electron, and they would screen. So the basic thing that we learned, 80 years ago, is that the most simple manifestation of multi-particle interaction on the renormalization, let's say, of 2 or 4 particle interaction is just a screening. It diminishes it. And in kinetics, we'll see that it's also always the same sign. If you, a little bit later, I'll say a few things about Boltzmann equation, but the same thing with Boltzmann equation. If you're looking at a scattering of classical particle, then you find out the existence of all other particles, namely multi-particle correction, essentially imposes a mean free path, namely that it restricts the region, how long you can fly before you can scatter at something, return back, and influence this other particle. But yet, at early 70s, it was discovered by many people that there could be a beta which is negative. And it was surprising. And it's still, I mean, it's not a very intuitive what is on a most fundamental level distinguishes one situation from another. In a sense, there are different ways to describe it, that there are different channels of interactions, not through real particle, but through some kind of, I mean, when you do quantum chromodynamics, in Coulomb gauge is kind of more clear. But anyway, technically, you find out that there are other physical systems in which interaction with other particle enhance the interaction of a given thing, right? And that's what we find out in the quantum chromodynamics. It's anti-screening, and it's sometimes called asymptotic freedom in the sense that it tells you, if you go into very, very small scales, that's where we don't know anything, right? There at small scales, interaction is very weak. Because at a given scale, when we measure it, it's already enhanced and it's finite, then it must be very, very small as we go towards very, very small scale. It's called asymptotic freedom. But on the other hand, it tells you that as you go to larger and larger and larger scales, your interaction is getting stronger and stronger and stronger. And at some point, the particle interacts so strongly that this denominator turns into 0 formally. It tells you it's like infinite interaction. What does it mean physically? Physically, it means that you're using a wrong language. That those things which you use, A's, those A's, which is the amplitude of your quantum field. In our case, A's would be just elevation of water surface. It's a wrong variables, because in these variables, your interaction is infinitely strong, which means that you need to find a new variables, which apparently will be a state of many, many plane waves, because I'm trying to describe everything in terms of plane waves. I'm doing Fourier expansion. And then I find out that for some system, it will be a wrong language. What would, yes? No, in critical phenomena, it's purely classical. Purely classical, you have fluctuation of different scales. You just integrate over this fluctuation. But you can do it for critical phenomena, and for critical phenomena, it's purely classical things. Namely, you ask how the fluctuations on all scales renormalize your parameters of your probability distribution, which is essentially Hamiltonian for equilibrium. Okay? So there's nothing specifically quantum. Quantum is what makes this fluctuation unavoidable. There is always quantum vacuum fluctuation. In classical system, you need to tune your system to criticality, and then you have this set of fluctuations. Okay? So now let me continue with my question. So if my plane waves aren't a right language, what is the right language? And again, from field theory, we learn what is the right language. That when we started with this description, we started that there are quarks and gluons, and they are weakly interacting. And all this formula, all this approach is a perturbative approach trying to account for this interaction with many more and more. What actually happens in some scales is they interact so strongly that what appears are hadrons. Hadrons, protons, neutrons are the right object to discuss. And they are very strongly bounded states of quarks. That's why it's called confinement. The other side of asymptotic freedom at small scales is a confinement at large scales. Namely, at large scales, you don't see this free quark running around, right? You need to build a multi-billion-dollar machine to see quarks running around, quark-gluon plasma. And this suggests to us that in our situation for turbulences, we also need to look first on the most basic basis on a separation of our turbulences into these two classes. And then, when we are fortunate to encounter beta, which is negative, to ask what would be the confined state, the strongly correlated states of many, many waves, and we can immediately fantasize about it. Okay, so now let's do computations. Let's tell us how much time. So you do, I mean, as usual, you write equation on a pair correlation function. You find out that it's expressed in terms of a 4-point correlation function. Its imaginary part, namely it's a cumulant. For Gaussian field, it's close to 0. You assume that you add a small forcing and a small dissipation to your system. You assume that at the end you will take a limit of f and gamma going to 0, but the ratio would be some occupation numbers. So you assume that your probability distribution is close to Gaussian. You do standard perturbation theory like you can find in any 31st pages of any field theory textbook or statistical mechanics textbook, etc. So you, in the first approximation, you just solve this equation. But one way is just to solve this equation in powers of your forcing, and then average over Gaussian statistics of forcing. So you get kinetic equation. As usual, as most things in science, this was a PhD student who derived it, Rudy Parels in 1929. And of course, it's very similar to the Boltzmann equation, because it also describes the scattering. These two equations could be considered as two limits of a quantum kinetic equation. In a quantum limit, you have particles, you have Boltzmann. In the classical limit, when the occupation numbers are very large, you get Parels' kinetic equation. Hasselmann got a Nobel Prize for deriving this equation and applying it to climate and weather. And Zakharov didn't get a Nobel Prize for solving this equation. Anyway, let me briefly remind you what you get for Boltzmann, because for Boltzmann, what I'm about to describe you was done 40, 50 years ago by many people, and they were actually asked what would be the next term correction to the Boltzmann equation. Boltzmann equation describes pair scattering. What if I describe a situation where I have my particle scattering on this particle, going out, meeting another particle, and returning back to this? it would give me correction to Boltzmann, which would be next order in density. Boltzmann equation obtained for very dilute gases, for very rare scattering. So these heroic people of late 60s and early 70s, they actually computed next correction. And what they found out that they diverge. Namely, if I look at the distance r, and I need to integrate over all possible r's where my second scattering will be, or where my third scattering will be. Then I find out that n's, when there will be n secondary scatterings, there will be rho in the power n, r in the power n, because this is n such things, and then I need to be back inside this small solid angle, which give me negative power of r. The larger r, the more difficult for me to get back to my particle. And then you realize that starting from n equal to d minus 1, my integral diverges in infrared, which is, as it has physical consequences. There are no one-dimensional kinetics in weakly colliding gases. The particle always in one dimension return to each other, and they interact strongly. In 2D, you find out that you have logarithmic divergences, and 2D is a very non-trivial, and starting from 3D, your corrections are truly small, but these divergences tell you that they are non-analytic. I won't go more further to it. It's now very well understood. We'll find out similar things. On the other hand, here we say, okay, but physics is really finite. Of course, when you account for multi-particle things, it tells you that this R cannot be larger than the mean free path. But mean free path is a collective effect. To describe it, you need to sum infinite series of diagrams. They call ring diagrams or bubble diagrams, many loops, but of a very special character. And then you get this formula very similar to what I wrote to you, lambda equal to lambda 1 plus beta will be positive. As a particle, diminish interaction of these two particles in kinetics always. I don't have simple explanation, but it's evident because the mean free path restricts your interaction. Now let's get back to, so what we want to do, next stage of kinetics, because essentially what people found in 70s, that if you consider correction to Boltzmann kinetic equation, they all finite for equilibrium. Equation of state has a regular virial expansion. When you do non-equilibrium, and what they did, they just computed kinetic coefficient, viscosity, diffusivity. They all have diverging terms. But what we want not very close to equilibrium and kinetic coefficient. We want a system very, very far from equilibrium and get correction to kinetic equation. That's why we call it somewhat a little bit a Stonguin-Chick, a postmodern kinetics. So let's do it. You just write a kinetic equation. You say what you expect. What is the analog of a small coupling, which will be here. And you say that this will be just a ratio of your quartic term in the Hamiltonian, which you can estimate like this, to your quadratic term in Hamiltonian. And you expect this quantity to be small. And at that point, you expect that your equation, kinetic equation, has this solution which Zakharov found in his PhD. And this is solution which is a steady solution of this equation. It turns it into zero, and it corresponds to a constant flux in space. It's a cascade solution. It's a solution which is steady because it has the flux going through the scales, energy flux in this case, constant. So the same solution incidentally exists for Boltzmann equation as well. So now, and you can find it in different books now. So what is important for this solution to exist is that the integrals in the kinetic equation converge, because you really need a cascade which is a local interaction. Namely, your most interaction must be with a comparable wave numbers, and this is imposes a condition on convergence. And fortunately for water waves, for example, it's convergent, and the Zakharov solution is indeed observed on the ocean. And then what we do with Vladimir, we go to the next order. So first of all, you renormalize frequency, and it find out to be not very interesting. It's still there. So your omega renormalize, it's your Bayer omega plus, it's the first term, this is just one loop, it's proportional to the waving. You see that it's proportional to the sign of lambda. Positive lambda, you increase your frequency, negative lambda is like attraction between waves, right? You decrease your frequency, you find out that there are cases in which this integral diverges. And yet, for example, for water waves, you find out that it converges. There is nothing non-trivial. These corrections are small as long as your dimensionless parameter of nonlinearity is small. And then we do lambda. Again, there are two diagrams in the first order, which are correction of lambda squared. And then you look at this correction, you find out that they diverge at UV, at very large P. They diverge at infrared. And also they contributed to kinetic equations, the dependencies of other wave numbers, 1, 2, 3, 4, which also could be divergent. So now you find out that there is the whole zoo of divergence. You need to analyze it one by one. Incidentally, I found it 40 years ago when I was a PhD student. And because I mean, I was given this kinetic equation and I just computed next term. I found out these divergences. I didn't know what to do. So I came to Zakharov, to other people, and said, yeah, well, there are divergences. Yeah, we know. But you know that C is not that large. I mean, that's not really kind of a big contribution. And it took for me many years and learning from people from field theory to understand that for field theories, divergence is a gift. It's an instrument. It's something which is not a nuisance. It tells you something about your system. And so 40 years later, after my PhD, I returned to it. And we started to analyze it. So first of all, this is just a correction to lambda. And again, you may ask whether it's positive, whether it's negative, whether it converges, whether it diverges. And I won't go into this much details with you. But first of all, for most interesting cases, including waves on the water, you find out that there are no UV divergences. Namely, that if your dissipation scale goes to zero, namely your viscosity goes to zero, your Reynolds number getting very, very large, the corrections of this finite dissipation scale are getting negligible in most cases. On the other hand, what you find out, and that what K naught, which is your lowest wave number, stands here, then this combination is very often positive, and it's positive for surface gravity waves on the water, for your storm. So in this case, you find out that your dimensionless coupling is not what you expected, but it renormalized by a large factor. Moreover, it tells you something pretty unexpected, namely that when you keep your level of nonlinearity at a given scale, namely your flux, your dissipation rate of energy fixed, but your K naught goes to zero, no matter how small is your naive dimensionless parameters, your waves are strongly interacting. This is really something which one may think it's truly unexpected. And yet, if you go back to incompressible turbulence, where, of course, we cannot derive anything, but we know empirically what is called intermittency, anomalous scaling of different waves. Namely, we may ask how the moments of velocity differences at a given scale R depends on the R for a given n. And what we find out that there is a dimensional estimate, P is a flux, which we usually call epsilon. So this is a Kolmogorov estimate, but we find out that there is this factor when L is 1 over K naught, is the largest scale in the system. And it tells us then delta changes sign at n equal to 3. All moments lower than 3, in particularly second moment, which is the spectral density of turbulence, goes to 0 when under a fixed flux, L goes to infinity. It's something which you probably all of you know. I just want you to appreciate the dramatic statement. So you keep a flux, right? You keep the rate of energy dissipation, but your large scale goes to infinity, and your turbulence level goes to 0. Because the system is very strongly interacting and strongly fluctuating, you don't need much turbulence to carry the same flux. The larger your system, the more and more strong and rare fluctuation can happen in it. That's what this delta tells you over here. On the other hand, when n is larger than 3, so you're asking for high moments, for high cumulants, they all go to infinity because delta is positive. On the other hand, there is no dependence on the dissipation wave number. So what I think we found in our system, just by considering first correction. We also computed two-loop correction, and we try to sort out the whole series. I won't go there. But in our case, it's really what we found out, that our corrections give us this kind of contribution, and this contribution is given by divergences, and the most important things is K naught over here, which enhances the interaction. Okay. Now the sign. Again, what will be for our wave system the sign of this correction? Whether it will be screening, suppression of interaction, or enhancement of interaction, like in quantum electrodynamics. So what we found out that when you look at this general integral, where is this dumb integral? Yeah, here is my first one-loop correction. It's complicated. I mean, this delta lambda is first is proportional to lambda squared. This is something which is always positive in a given region, but this is something which could change sign. Moreover, for a normal physical system, for example, for surface gravity waves or for capillary waves, bare lambda changes sign. Some waves really attract each other and some waves repel each other. It's a complicated system. Now you have complicated integral over all of them, but you can look at it in the limit, and in particularly when you look in the limits, here. When you look at the limits, you find out, limits, I mean the interaction of very long and the very short waves. You find out that the sign of this correction is determined by the sign of your original lambda, which you would expect, proportional to second derivative of omega with respect to wave numbers. And this is something which we know very well. It's a Bogoliubov formula for fluctuation of a condensate or modulational instability of a given wave, or criterion for existence of solitons. If your lambda omega 2 prime has opposite signs, it tells you that you can have solitons in the system, that your nonlinear interaction could be compensated by your wave dispersion. Here, it's more generally, it tells you that there are physical situations in which your sign of your bare interaction and sign of your dispersion are different, where you enhance the interaction, and it tells you that you may have confined states. And those confined states aren't necessarily solitons. They could be, what is this? What is that? What is that? It's a cusp. It's a breaking wave. You see form, which was already a result of a breaking. There are different exacts, like there is Stokes wave, which has 120 degrees. But this cusp is like hadron. It's a bound state of many, many, many waves, right? To organize something like soliton or even Burger's shock is a coherent state of many plane waves. So in a sense, and we did not compute yet sign for gravity waves. We're working on it. It's a very complicated integral, even though it's a given integral. It's very complicated. And it has zeros, it's Cauchy value integral. So now, about to finish all this story, what is, and again, nobody did it yet for Boltzmann. So what I want to make a take-home lesson here is that you can do a relatively straightforward perturbation theory. Again, you cannot do it with incompressible turbulence because you don't have a linear churn. But for cases of wave turbulence where you have frequency, you can start from a very weakly nonlinear regime. You can do regular perturbation theory. It teaches you very important lessons, which for some unknown for me reasons that we did not do 40 years ago. I don't know, Zahara with Polyakov did not do it 40 years ago. And we learned the following things. First of all, we learned that indeed we can divide our wave turbulences into two classes, with enhancement and with suppression of interaction. And when we see enhancement of interaction, we can guess that the state of a strong turbulence, which appears at some scales or somewhere down the cascade, will be determined by bound states, which again is nothing new. We know Burger's turbulence. Burger's turbulence is, its statistic is determined by bound states. These bound states are just simple shocks. Now we realize that in other cases, we also can have this, and maybe the first time we have an analytic grasp of it. Still very complicated, but opening a window. Thank you very much. Ready for take questions.
Time for questions.
I have a very simple question. From what you are saying, wave turbulence is a two-dimensional problem.
No, I mean,
because waves are on the surface. It's
C wave, but spin waves are three-dimensional problem. Plasma waves is three-dimensional problem.
What you just described, the C waves, looks like two-dimensional problem, and I'm surprised it's not exactly solvable. Or two-dimensional field theories are classifiable, and they are all belong to solvable classes, which are very well known, unless this is a non-local theory.
Yeah, it's a very good question. First of all, something which tells you how different it is, dimensionality is totally irrelevant in all these situations because you find out that your turbulent solution is always have k in the power minus d, so even your level of nonlinearity is dependent on dependence. Still, Sasha rightly asked, in 2D we always have something like conformal invariance, which is infinite dimensional group. Could we have conformal invariance in this case? I never published it. Actually, we proved with Zamolodchikov that if you impose Zakharov solution, you cannot have conformal invariance because the structure of your triple or force cumulant, something which precludes conformal invariance. So wave turbulence with a non-zero flux could not be conformal invariant even in 2D. Is this probably I need to write it somewhere? Okay?
Is it because of incompressibility?
No. Here it's you can do it for acoustic turbulence. You can do it for spin waves. It's just that cumulant, which is a flux, it breaks. Conformal invariant is essentially time reversible theory. Conformal theory, time reversible. Here's a cumulant. The fact that you have a cumulant which is flux, you cannot have such cumulant in conformal field theory. Like your triple moment always a product. No such luck here, right?
I think there's a question there.
Hi. I wanted to follow up on the comment I made before. You see, in the classical equations of motion, in one of the earlier slides for the modes AK, you introduced some noise term, right? Or
yes.
You did that, right?
Yeah.
Yeah, so I just wanted to ask you, I mean, that's essentially the sort of point I was making, that you have to modify the classical equations of motion. And so may I ask, that noise, I think the one you're using is Gaussian noise, right? Local?
Yeah, because
Why?
I'm working with perturbation theory, so I'm assuming that my system is close to Gaussian. So I impose external noise Gaussian. But it's a nasty thing. I want to do it differently, really. Yeah, differently, you would start from initial state, which is Gaussian, let it interact, and ask what will be a long time limit. Nobody did it. It's very difficult. It's probably doable. Yes.
Yeah, I have very much related questions. I mean, these are classical equations of motion, but you never told us what are the initial conditions. Yes. And so I just wonder, when you do this, say, wave turbulence or this kinetic theory, what are the initial conditions you're putting in?
Yeah. So because I'm imposing an external force, then my initial conditions are forgotten. I can forget about it. But this external force is a very artificial device. It's possible. What I really want to do is start from zero initial condition, start forcing which is at large scale, start from it, I don't know, some initial maybe near Gaussian noise and see where it comes. And it could come in a state which is very far from Gaussian statistic. It can grow cumulants with time. Nobody did it.
So I had a question. So if you take this theory, this wave kinetic theory that you're doing, and if you couple it to some kind of a probe particle, yes. With some size.
That's exactly what we are doing, yeah.
So with some size, which kind of puts some kind of an IR cutoff in the sense that the particle can only feel certain scales because of the size. Then, would you get a similar kind of running and so on and so forth?
We don't have particles, we have waves, but we have a restriction of sizes. We have pumping scale, it means there is lowest wave number, and we have a dissipation scale, which is the largest wave number. So we studied their influence. But on the other hand, we do make probe in the sense that I'm just taking 4 waves and ask how they interact when there are many, many other waves around. So this, you can say that this is a probe. This kind of 4 waves interacting.
Yeah, so just one follow-up question. So if, you know, for example, if one of the waves that is interacting is a very high wave number, whereas others are, you know, or basically two are very high wave number. That is, you have a very high wave number scattering against a smaller wave number.
Yes.
Do some simplifications.
Yes, exactly. I derive my criterion, how I distinguish QED from QCD, by considering this very high, very low interaction. That's a limit where I can get a really simple analytical formula for vertex renormalization. Exactly in this limit. Yeah.
Okay.
Absolutely.
Thank you.
Yeah.
So let's thank Risha again for a wonderful talk.